Okay, here's another key idea video or key concept video, but this time dealing with the idea of uniform circular motion. So in the lectures, what we did was to describe the motion of a particle executing this uniform circular motion. So the key idea here is that this is at constant speed, okay? And we derived those equations for the velocity and acceleration based just on a sort of geometrical understanding of this system. So what we did was to say, well, this is our position vector. We got some angle there, theta. And the key concept, so the thing that I want you to kind of take away, because from this you can derive everything that you need, the key concept is that the velocity vector is perpendicular to the position vector, okay? And that's because the velocity always acts in this tangential direction. And that's because if we were to zoom in on this little region here, effectively what we would see is something which looks like a straight line, okay? If we zoom in far enough, what we'll see is the particles moving along this, and this is part of the circular arc. But of course, it's moving in a direction that is kind of tangential to this position vector there. So that's the idea, is that actually these two things are perpendicular to each other. So if you remember that, that's great. In the lectures, what we did was basically to write down what this v was in terms of the kind of geometric understanding, and then from that derive the acceleration. I want to show you a slightly different derivation this time, which is based on the idea that the thing that's really varying here is this theta. Okay, so if we take account of that and then work through the mathematics, then we can derive what this velocity is in terms of or via the root of looking at theta. So the point here is that if we look at the coordinates of our particle in terms of r and theta instead of in terms of x and y, then this r isn't actually changing, okay? Because the size of this position vector remains the same, okay? It's always moving around on this circle, so it's always exactly r, the radius of that circle, away from our origin. So this thing isn't changing. This thing, on the other hand, is changing all the time. And in fact, it's changing at a constant rate because theta just grows and grows and grows as I go round and round and round. So theta here is a function of time. And what we actually do in order to start this is we define some quantity which we call omega, which is the angular velocity. And this is a concept which is quite important for describing this kind of motion, but in the lectures we didn't actually cover it because we just described everything in terms of the kind of linear velocity v. Omega is the angular velocity, and what that means is that omega is the rate of change of this theta with respect to time. So if you define the angular velocity in that way, then we can use this quantity anytime we need to take a time derivative and we see theta appearing there. Now, the other thing to note about this is the angular velocity is essentially like the angle, the change in angle as a function of time. And you can see that, right? That's what this means, d theta with respect to time. But this is obviously going to be related to the linear velocity, which is essentially this v vector here, by virtue of the fact that both are changing as a function of time. And if you think about what happens here is if you're very far out, okay, so if you get further and further away from the center and you're still moving at the same angular rate, okay, so you're covering the same angle in the same amount of time, then you're actually traveling much farther, okay? So you're traveling a larger linear distance because the circle that you're describing is much larger. If you're very close to the center and you're moving at the same angular rate, well, the actual distance that you're covering is much smaller. So what that means is that although the angular velocity is the same, the linear velocity will depend on the radius. And it actually turns out that these two things are connected. The linear velocity is equal to the angular velocity times the radius. Okay, so if my radius is very small, then for the same angular velocity, I'll get a much smaller linear velocity. If my radius is very large, for the same angular velocity, I'll get a much larger linear velocity. So this relationship is also important, and we can write it as omega equals v over r. Okay, and these I've just written these are scalar quantities here because this is based just a relationship between the angular speed and the linear speed. So with these tools in hand, we can now set about actually deriving what we need to derive. Because of course, we wrote down earlier on in the lecture today that our position if we want to describe it in xy coordinates, so just going back here, if I now draw on an axis here, I draw x and y, the position here, this x coordinate will be r cosine theta, and the y coordinate there will be r sine theta. So let's write those down. It's the same starting point. So our x coordinate is that, our y coordinate is r sine theta. And what that means is that my position vector r can be written as r cosine theta I plus r sine theta j. And here I'm writing r without the line underneath it just to indicate the modulus of r, or the kind of scalar version of r. Now, in our very first week, one of the key concepts that we covered is the idea that the velocity is the rate of change of position, our position vector. So what that means is that we need to differentiate this quantity here that we've written down with respect to time. Now, what you'll notice is that there isn't actually any explicit time dependence in this expression. But of course we know that this theta, that depends on time. And what that means is that we have to apply the chain rule. So if I want to differentiate this expression with respect to time, what I do is I differentiate it with respect to theta, and then multiply by d theta by dt. Okay. In other words, let's write out what that means. Okay. So we have v is equal to d by dt, or dr by dt, which is the same thing as doing dr by d theta multiplied by d theta by dt. So now we can differentiate this expression up here with respect to theta. We know how to do that. And we also know what d theta by dt is. We defined it over here. It's this angular velocity, which is also this v over r. Okay, so this is equal to d theta by dt. So anywhere we see d theta by dt, we can substitute in v over r. So let's do that then, and we'll get an expression for the velocity. If I differentiate this with respect to theta, what I'll get is, well, the r is a constant, so that remains. If I differentiate cosine theta, I'm going to get minus sine theta. So I get minus r sine theta I. But that's just differentiating with respect to theta. Now I need to multiply by d theta by dt. So let's put that in there. And then for this term, we'll do similarly. So r is constant, so that just remains. And when we differentiate sine theta with respect to theta, I'm going to get cosine theta. So I get r cosine theta j. And again, multiplied by d theta by dt. So what we've done is we've taken our r and we've substituted it in here. We've differentiated with respect to theta, and each term then we've multiplied by d theta by dt. And then I can replace this d theta by dt here with the v over r that we defined over here. So this is v over r, and this is v over r here. Okay, and then we can cancel out the r's here and here, and we get that the velocity vector is this velocity, or this speed here, which is the magnitude of v multiplied by sine theta I, or minus sine theta I, and on this in this term multiplied cosine theta j. Okay, so v, our velocity vector, is minus v sine theta I plus v cosine theta j. And what I'll point out is that in the lecture, when we just treated this, when we use this key concept that the velocity is perpendicular to the position, we were just able to derive that fact geometrically. Okay, so we just use the fact that we've got some j component of the velocity acting up here, and that's just going to be v cosine theta, and we've got some I component here, which is going to be minus v sine theta, and that's exactly what we've arrived at by using this chain rule and differentiating our position with respect to time. Okay, so this is the same thing, and from there the rest of the derivation proceeds as we did in the lecture. So the acceleration, and again, one of our key concepts from last week, acceleration is just the rate of change of velocity with respect to time. And again, we can differentiate this expression with respect to theta, and then multiply again by d theta by dt, remembering that d theta by dt is just v over r. All right, so let's do that just one more time then, just to see. So when I differentiate this with respect to theta, I'm going to get minus v cosine theta, and then I'm going to have my v over r, and that's in the I direction. And this one then, we're going to get, when I differentiate cosine theta with respect to theta, I get minus sine theta, so I get v sine theta, again, multiplied by d theta by dt, which is v over r, and that's acting in the j direction. And so I get minus v squared over r times cosine theta I plus sine theta j, exactly as we did in the lectures, showing that this acceleration vector then actually acts in exactly the opposite direction. So I've got this minus sign here. If you remember what r was just r cosine theta I plus sine r sine theta j. So you can see that the acceleration has got this negative scalar quantity multiplying by the same, a vector in the same direction here. So this is just in the positive cosine theta plus sine theta j direction. This is in the negative cosine theta I plus sine theta j direction. So the acceleration acts contrary to the, in the opposite direction, basically towards the center of the motion. So that's, we've arrived at the same point we did in the lecture. All of the same stuff that we covered there is still valid, but I just wanted to show you how we can invoke this idea of the angular velocity in order to arrive at the same point.